Hello, YouTube audience. I'm playing around with the system here, so the lighting, we'll see how the video system goes. I'm trying to stand back, stand forward. I'm using a laptop camera, so it's going to be just a little bit difficult to get the right. I'm not that well angled and well proportioned anyway. It'll be probably even more difficult to really get this down right, but I hope that it's the intellectual content that counts anyway. This is my video that I'm doing after my famous or perhaps infamous open mic presentation, open letter in a sense to Professor Stephen Hawking, a very respectful and very polite disagreement with him about the notion that cosmology leads to reductionism. I think that if anything, cosmology leads away from reductionism. However, that's not really what I want to discuss today. I want to kind of break away from that subject. I respect Professor Hawking. I consider him not only a great scientist, but a great human being. Somebody who's overcome tremendous difficulties and is an inspiration to us all, because remember, there are very militant survivalist, social Darwinist doctrines about, why do we invest so much in people that they would consider, quote, unfit. Well, Stephen Hawking, he had a terrible disease, obviously, and still does. And look at the contributions that he's made to physics. In some sense, it's kind of strange that he would embrace radical reductionism because his own life is a stinging rebuke to radical reductionism. It punches holes right in radical reductionism and a lot of the philosophies such as social Darwinism and militant survivalism, and a lot of the philosophies that have gone together with reductionism. It seems as though Stephen Hawking's own life is the fact that in spite of everything, he's still been a brilliant physicist, a brilliant cosmologist, that's been almost like it punches a hole in a way in the whole argument of reductionism. But all right, let's leave that aside. I want to get to a few more. I want to punch another hole in reductionism, and I want to address the idea of classical physics and determinism. That it's often been stated that classical physics is inherently deterministic. When you have philosophers like Dennett, they seem to want to go back to the pre-quantum world and go back to 19th century physics and say, okay, maybe this newfangled quantum, new age mumbo jumbo, maybe that's can have something like free will, or maybe that can punch a hole in determinism. But that old 19th century physics, good old-fashioned Newtonian physics, that has to be deterministic. And even though Laplace and the three-body problem, even though there are various aspects of classical physics that might seem to negate that, there's never really been a good argument to say that even classical physics itself, I would say that the whole idea of determinism is unknowable according to classical physics. And I want to make a case for the idea that classical physics, you can't say whether it's deterministic or not, that it's unknowable. And I'm going to bring in Cantor, as I often do, because Cantor, frankly, came up with what he came up mostly during the bridge between classical physics and then later on in his life, relativity and quantum physics. But his discoveries about levels of infinity obviously transcend either classical physics or relativity. They are true, and they would be true in a universe of classical physics also. Okay, let's say we want to understand whether a classical system, we'll call it set U, is deterministic or not. Well, obviously we would have to break it down into discrete units, right? And what better way? We break it into half, we break it into fourth, we break it into eighths, sixteenths, 32s. Eventually, I don't know if I would. Yeah, okay, all right. But eventually we would get down to an infinite number of discrete, we can call them infinitesimal points, that would make up set U. And at each division, we know everything about the position, the momentum, velocity, everything that we would know, acceleration, all the forces that are acting on each one of these different maenads, or each one of these different units. And we keep going more and more to ever more discrete units where we know all the forces that are acting in that given space within set U. Whether there's empty space, whether there are particles. Again, this is not possible according to quantum physics, but it would be possible according to classical physics, and that is then used to say, aha, well, classical physics is deterministic because we can break it up into ever smaller pieces and ever smaller chunks until eventually we get down to a maenad or an infinitesimal. And there we go. We know all the forces that are acting on each infinitesimal. And with an infinite amount of knowledge, we can know the past, well, if we know the past and present, we would know the future of the entire system.